Good morning to all. My topic is on Doppler effect. So I am doing my DA3 assignment as part of my course part. So we will be going through the Doppler effect, and I am going through the slides now. So we are seeing the radar in many autonomous systems and day-to-day lives we may come across. But we may not have a good idea about what is radar, and most of the people have not understand the full potential of how radar system currently works. In this presentation, I will be detailing about radar and its processes and how it is implemented in the systems and how it saves a multi-million peoples from any defense attack. So we will be going through these slides. So initially, I will start with a brief introduction how radar works and how is the methodology and what is the methodology used in radar detection and ranging, and then we will be going through frequency modulated continuous wave radar. Frequency modulated continuous wave radar is a type of radar which is used in most of the autonomous system, self-driving cars, drones and other vehicles also. So we will be going through that. And then Doppler shift, Doppler radar and its working, beat frequency, frequency modulation and demodulation, and radar equation and its components. So we will be going through the fundamental parts of radar, and we will be going through the applications and everything. So initially I will introduce myself Rohit. Currently I am pursuing my MTech degree in VIT Chennai. Previously I worked for 3.5 years in Emerson, which is a conglomerate in automation technology, and I have been handling application engineering department of control valve sales and service, and I hold a bachelor's in mechanical engineering degree. So let's start with the question. What is radar? Radar is radio detection and ranging. It is an acronym, and radar is being developed in 1940s. Initially at the World War II period, England has developed this radar technology and used in their navies. So after that we have been going through multiple evolution of radar, and currently in industry 4.0, in industry and in autonomous vehicles and in many different parts of defense and even in aerospace industry, aeronautical, every other industries, radar is a viable technology. So referring to this slide, we can see a drone here. A drone uses a radar technology to map the geo positioning, and if there is any, like, it will geo map like what are the places which it can go, it is free to move, and at what height it is traveling. So every other parts can be detected using radar. So as part of the slide I can read, like, radar is used in blind spot detector, rear collision warning and adaptive cruise control. In automobile technologies, we can see these punch points very clearly in most of the Tesla self-driving cars and Volvo. You see, Volvo is one of the company where zero accidents have been happened. So this can be achieved only through radar technology, and we will be going through it. So as I said before, it is a radio frequency detection and ranging. So it will send radio waves, and once it use the principles of reflection, and it will detect any movement or any velocity, any object intervention, it can be detected. So as the slide says, you can see here, this is one aircraft which is flying over the area, where the station unit can check whether the flight is crossing it or not. You can see that the Blackbird of US air defense has been highest top speed aircraft. Even that aircraft can be detected using radar. Initially, if you want to check about the Lockheed Martin air defense system, you can check it out. So let's see about the formulas. So range is the distance from the radar site to the target measured along the line of sight. So you can see here, we know that as per the formula, velocity is equal to displacement per unit time. Since the radio waves travels at the velocity of light, you can see the C naught is the speed of light and 2r is the distance traveled by the radio waves, and t is the time taken for the radar for sending the frequency and receiving the frequency. So that is the time taken. So using this formula, we can able to find out V2r, which is the distance, and we will be seeing through a lot of equations wherein which how the radar is detecting and how it is like how the complex process works in the single chip. We will be going through it. So the factor for 2 in the equation comes from the observation that the radar pulse must travel from the target, and once the target once in the target, when the frequency is reached, it will get reflected and it will travel it back. So the 2r resembles the travel from this position and returning to the fourth position. So as we see here, we can find the range from this formula. So okay, we have seen, I have been talking more about the autonomous vehicle and its how radar is being used, how the frequency is transmitted, and we have seen that. So now we will be seeing about what is a practical application and how it can be implemented. Because if a technology is to be viable to even to the down earth citizen, it must be viable and it must be cheap so that they can use. It's not that only a certain path, certain people alone can be grown with the technology. The technology should be viable to all, then only it can flourish. So same as like that, the radar technology also, to be practically implemented, there are some constraints. So we can see here like low cost, low power and small form factor. These are all the major constraints. So what is small form factor means? It must be very small, very handy in size, so that it can be easily transported. It should not be like a very big station of huge weight. Then the sensor or the system will not be a practically implemented system in a small vehicle like drones. So in case if you want to use it in drones, which is already a very small equipment, so if you want to use this kind of radar, then you have to design in such a way that it is a very small radar and it can be designed so and so. So this can be achieved through multiple level of iterations and designs. So we will be seeing about multiple radar types and we will be going through each one. So I will read through the slides. Achieved through mass production, low cost achieved through mass production, simplified circuitry and the use of the self components, and low power utilizes efficient signal processing and low power transmission techniques. Since if you are using it for a drone application, then low power is a very must important thing, because if you are carrying a heavy battery, then the payload itself will take much energy and it will consume lot of energy, power from the battery, and it will not be a good thing for the motors to run, right? So we will be seeing like how these requirements are met with the current industrial radar, and we will be going through it. So yes, so as I said before, there will be types of radar which we will be seeing, and the radar is that the waves will get transmitted and it is reflected and then received by the transmitter. So that's how basic principle works. So with that radar principle, Doppler effect, this effect is called Doppler effect, which we will be going through. With this only, bat and dolphin and some other animals also using these technologies. So yes, so let's go through the types of waveform, like what are the waveforms and how it works. We will be diving into each and every part. Continuous wave, a constant frequency and amplitude signal without interruptions. So you can see here, in this continuous waveform, wherein the transmitter will generate a continuous wave of oscillator frequency. it is a constant frequency, that the radar will generate a constant frequency, and that will be hit by the object and it is received. So this process is so continuous that there will not be any gap. So like in the slide says, a constant frequency and amplitude without interruptions. There will not be any interruptions in between, and it will be just like the sending the wave signals alone. And this is a radio broadcasting. This example is a radio broadcasting that we will be seeing. Like we have our stations like the Suryan FM and some other FM, right? A constant frequency 93.5. It is nothing but 93.5 is just the value of the frequency. So, and let's go through the pulsed wave. Okay, in this pulsed wave form, the frequency, as you see here in this diagram, it is a pulsed frequency. Only a pulse of the frequency will be transmitted. That means in the slide before you can see an image, right? In this radar image, you can see here a certain pulse will be generated, and this pulse alone will get reflected again. But in case of continuous radar, a continuous wave will be traveling here. But in case of pulse, a certain pulse will be sent, and that pulse alone will get reflected. So you can see in this GIF image. So as in this slide says, a sinusoidal signal transmitted in pulses. It's an on-off pulses. Okay, this sine gated wave by a pulse train, as I said. So this okay, it is used in the radars, in sonar, and medical ultrasonds also. This kind of pulsed waveform. Yeah. So as we have seen the pulsed wave and continuous wave, but these waveforms cannot be directly implemented to our radar system. So we will be seeing why these systems cannot be directly implemented and how it can be implemented. So as in the continuous waveform, radar can measure the velocity but not measure the range. Since the waves are being continuously transmitted, it cannot able to measure the distance. It can only measure the velocity, like on what velocity it is moving. That derivation we will be seeing in coming slides. So please keep in mind that this continuous wave radar can measure only the velocity and not the distance. So velocity tells you how fast an object moves, but does not explain its starting position or path. Yes, but in case of frequency modulated continuous waveform radar, the frequency shift helps calculate the distance by measuring the time delay based on the frequency difference. So this, okay, you may feel like, what is this frequency modulated continuous waveform? So I will detail you like what is it and how it is used. So this frequency modulated continuous waveform, it is a particular waveform wherein it's as similar to the continuous waveform. This is also continuous, but only thing, on the continuous waveform the frequency is constant. But in case of frequency modulated continuous waveform, the frequency is modulated. You can see the frequency versus time graph, whereas the frequency is continuously changed, and this principle can be used in the radar to measure both the velocity and the distance. So as in the slide says, the FMCW radar, the frequency shift helps to calculate the distance by measuring the time delay based on frequency difference. So measure the time delay based on the frequency difference. Yes. Okay. Then, but in case of, so let's see why a pulsed waveform cannot be used, because pulsed waveform also both the distance and the velocity can be measured. So let's see why this cannot be used. Pulse waveform is ineffective for shorter range measurements, because for a very short distance, let's say if a drone is getting near to a particular obstacle, if it uses a pulsed waveform, since a short range measurements, because one pulse of trailing edge and next pulse beginning edge could overlap. Since the distance is very short, one pulse range and another pulse range will overlap, and this can cause inaccurate measurements and it can lead to damage. So to avoid that, it can also create blind spots. As in automobile, there will be a blind spot, right? You can see here, if in case it is a car moving here, there will be certain blind spots which it cannot detect. So similar to that, this pulsed waveform will be effective for a local station, like in case of defense station, pulsed waveform can be used, but though it cannot be directly implemented with the technology, there will be certain modification implemented. But in this presentation, I will be going only through frequency modulated continuous waveform, in which it is widely, since it being widely used in many of the automobile sectors. So this is continuously varies its frequency, enabling accurate simultaneous measurement of range and velocity with high resolution and minimal interference. So we will be going through how this process is done and how it is simulating the result. So yes, so if I am explaining about frequency modulated continuous waveform, and if I am not explaining about Doppler effect, beat frequency and frequency modulation, then this topic will not be completed. So I will explain all these terms and we will be going through each and everything. So yes, we have seen Doppler effect in many circumstances, but we have not clearly identified it. So as you see in this slide, the Doppler effect helps in determining the direction and velocity and also the range. So if you see in this radar system, there is one radar system in the ground, and if there is any target approaching it, so if this transmission and receiver antenna sends a particular transmitter frequency, since the object is flying over it, right? So this object is already in a particular velocity, and if we are particular velocity in the sense, it is also having some frequency, right? So when this transmitter sends the frequency to this object, the frequency will get the frequency wave will be hit by the object and it will be returned back. So this will have a frequency transmission plus frequency detected. So there will be some frequency imparted onto the transmitter frequency. So you can see that Ft plus Fd. If it approaches towards the transmission receiver antenna, then the frequency shifted towards the positive side. And if the aircraft travels away from the radar, then a certain frequency will get detected, that minus to the receiver antenna. So you can see in this diagram, right? So transmitter Ft, but the return is Ft minus Ft. You can see if a person is standing here and an ambulance crosses, if it is approaching the person, then the frequency will be high. If it is as the car travels, as the ambulance travels, the person might hear a low frequency. Same as like that. So if an object the target is stationary target, so then the transmitter frequency and receiver frequency will be same. So this is how the basic principle of radar works, and how Doppler effect and the frequency which is transmitted to the frequency received as an impact, like Ft plus Ft, Ft minus Ft. So we have seen like how direction also impact the receiving frequency. With that, we can able to find the distance and velocity. So we will go through how the formula and everything now. Okay, so as I said, the Ft value and Fd value will be one of the components useful for us to calculate the velocity and distance. So, but you can ask the question like the transmitted frequency, which will be about gigahertz, but the object will be traveling with a velocity of, let's say, 100 km per hour, which is comparatively very low, right? So, but it like some kilohertz. So the difference of measurement, like Ft, this if you are plotting in a time graph, so let's say an object is getting hit by a very high velocity, there will not be major difference in it. So as I continue to speak, so this part refers about the Doppler effect and how it measures the direction and velocity. So as the antenna sends the transfer the frequency, and if the object is moving towards the antenna, then frequency increases. If the object moves away from the antenna, the frequency decreases. So if the object remains stationary, the frequency remains same in continuous waveform frequency. So next, if we see here, so there is some calculation involved. The transmitted frequency will be in gigahertz, and the received frequency will not have a major difference, because if you see an object, if it's moving with 100 km per hour speed, and if you measure the frequency, the transmitted frequency is of gigahertz, then if you even add that value to the gigahertz, there will not be any major change, right? So I have put a small calculation here. To calculate the Doppler frequency shift of an object moving at 100 km per hour, we use this formula, delta F is equal to 2 into V into F naught by C, where C is the velocity of light, and V is the object velocity, and F0 is the transmitted frequency. So using this formula, we can calculate that the frequency change is 185.2 Hertz, but the frequency which we transmitted is about 10 gigahertz. So even if you add, that's what I have mentioned here, even if you add 10 power 9 to 185.2, then there will not be any major change, right? The difference between the transmitted frequency and received frequency will not have a major difference. So while calculating the computing this value, the value remains very less, and if our radar has accuracy less than even 0.01% also, then the object will not get detected. So how the object is getting detected will be a major question to us now, right? So that's what I have mentioned in this graph also. Measured in gigahertz, even if the object getting detected, the frequency doesn't change much, right? Also measured in gigahertz but shifted to kilohertz. So you can see the difference is 10 power 6. So let's see how this error can be handled. Yeah. So as I previously mentioned, there are three important factors like Doppler effect, beat frequency, and frequency modulation. These three parameters may play a major role in determining the velocity and range using the radar. So as you see here, I just assume that, let's say, if we take a sine wave of 100 Hz and another sine wave of 110 Hz, and like if an object is getting hit to the object which is traveling towards us, then the frequency gets increased, right? So this increase in frequency or any change, the difference in the frequency can be defined as beat frequency. So that's what I have mentioned here. The beat frequency, FB, is the frequency difference between the transmitted and received signals in FMCW, that is frequency modulated continuous wave radar, caused by the time delay due to the target range. So as the target is moving towards us or away from us, the frequency getting changed, right? It will either increase if it is coming towards us and decreases if it goes away from us. Okay. So there will be some difference, and this difference can be calculated. If I am overlapping this sine wave to another sine wave too, then the difference will be very less. Even if you put in enlarged magnified form, the difference will be very less. And so to calculate the difference, we will use this beat frequency in a multiplied sine wave form. So if I multiply both the sine waves, then 2 sine A cos A is equal to cos of 2 sine A sine B is equal to cos of A plus B minus cos of A plus B. So using that formula, we will get arrived to a new sine wave form. This is a multiplied sine wave form, multiplied of sine 1 and sine 2. So we will get a good frequency graph here. So with that graph, we will be able to identify the small difference also. We will see in coming slides. So this graph will detail you in a very clear format. So if you see here, the transmitted signal frequency is 100 gigahertz, and if you receive a frequency of 108 gigahertz, then the beat frequency value is 8 gigahertz. Right. So that's what here it will be mentioned. If you can see the blue color line, it is the receiver line, and black color line is the transmitter line. So if you see here, both are of same waveform initially, and then the phase change will happen. The receiver end will have higher frequency than the transmitted waveform. So if you see here, at certain points it will get overlap here, here and here. So these indicate the highermost point of the multiplied waveform. That is, the beat frequency will be higher here. So this can be higher because of A as B. So both the frequency will get added. And in case if it get minus, then A minus B, it produces the beat frequency. So this is the main important thing of beat frequency, where in which we can calculate the difference, and with the difference we can arrive the range and velocity. As I said before, the beat frequency, however, the beat frequency can be separated using a low pass filter. Since, as I already told, if we are about to calculate the difference, since if we are intended to calculate the difference, that is 8 gigahertz, we can use a low pass filter, and we can remove the 100 gigahertz, that is a transmitted waveform frequency. We can remove using a low pass RC filter, and we can calculate the beat frequency value. Okay. As the frequency difference increases, the beat frequency also increases. So as I told here, if the distance increases, the beat frequency is proportional to the object velocity. If the object velocity increases, the beat frequency also increases. So based as the beat frequency, the A minus B value will get changed. So we will get a proportional value, right? So, but here also we have a small problem here. So that I will tell you now. See, if the value of F1, that is the transmitting frequency, and the receiving frequency F2 have 80 Hz and 120 Hz respectively, and similarly, let's say if we are having the same transmitting frequency of 120 Hz, and if we are getting a frequency of 160 Hz, see, you can ask a question now. These both have the same frequency difference, right? Then how it can able to detect the object is either preceding or succeeding, either traveling towards the object or away from the object? We cannot predict, right? We can predict only the velocity. With velocity alone, we can't able to find the object is like traveling towards us or away from us. So in order to calculate whether the object is moving towards us or away from us, we will use and compute this graph to a real and imaginary part. So as refer to the real and imaginary signals, we can refer the imaginary quadrature signal will move, preceded or succeeded the real phase. The real phase part will remain constant, and if we are changing, if the frequency is positive, then it will have a positive phase change, and frequency change is negative, it will have a negative phase change. So the imaginary part of the quadrature signal helps to decide us either it is preceded or succeeded, the frequency. So as I told here, we have discussed about the Doppler effect, and we have discussed about the beat frequency part. Like we have identified either the object is moving away from the antenna or towards the antenna. So we will have a short recap here now. Okay. So as I discussed before, the Doppler effect and beat sensor. So the Doppler effect, the change in frequency of a wave as observed by a receiver moving relative to the source of the wave. Okay. The key, as I told before, like if I make the sound here now, and the sound change will happen, right? But the amplitude remains the same. But I am creating a sound. You will experience the sound wave to have a different frequency relative to the receiver of it, right? So that's what Doppler effect means. So frequency increases when the source and the observer move closer, and frequency decreases when it moves apart. Simple, right? So the beat sensor, as I told, the beat frequency can be calculated using it. The FMCW radar, that's like I told, right? The frequency modulated continuous waveform radar. The beat frequency is the difference between the transmitted and received signal caused by the time delay. Yeah. And Doppler shift, I also told, the relative velocity of the target caused by it. So now, till now you can have a question like where is the modulation part comes from, and what is the problem which we are facing? Why not we can use the continuous waveform itself? So that can be the question. But still, if you see here, the radar will just transmit the signals and receive the signals. So it will continuously transmit and receive, and there is not a definite standpoint which we can have. That with respect to an observing value only, we can able to calculate the distance from the object to the receiver. So we should have an observed value, right? Distance doesn't provide Doppler shift, but velocity does. Velocity is the main reason why the Doppler shift happens. So since there is no defining characteristics concerning the distance and time along the object move, we need frequency modulation. So in frequency modulation, the frequency changes. So with respect to the preceding and succeeding frequency, we can able to identify the distance traveled along the given time. So here comes the frequency modulation. So if you see here in the graph, it has clearly put with y-axis on frequency and x-axis on time. So with respect to this, if you have a constant frequency line, so it will check the beat frequency that I have already told, right? If the object is the frequency increasing means the object is traveling towards us, and frequency decreasing means object is traveling away from us. So here we have constant frequency, but with respect to the distance we don't have any definite standpoint, right? So this triangular waveform will help us to have a okay, here the total beat frequencies mentioning that 8 absolute standpoints with respect to which we will calculate the time taken for the object to travel with respect to frequency, that means velocity. So triangular frequency modulation (TFM) is a technique used in frequency modulation waveform radar where the transmitted signal undergoes a triangular variation. That means the transmitted signal here, the transmitted signal which is sent through the antenna is traveled here through various ups and downs. You can see there is a triangular waveform, the frequency getting modulated instantaneously each and every time. So we will have an instantaneous change. So we can able to represent even if multiple objects are surrounding, multiple waveforms are going on the air. So we can't able to predict the particular waveform, right? So in order to detect a certain waveform and to eradicate the noise, we will have this triangular modulated frequency. So where the transmitted signal undergoes a triangular variation in frequency over time. So this method improves radar performance by offering a more efficient way to measure both the range and velocity of the targets. So with that, we can able to identify with respect to like here 8 node 1, 2, 3, 4, 5, 6, 7, 8. So we will get a comparative analysis over the preceding and succeeding signals. So even if like say a particular car is moving and another 2, 4, 3 it cars are moving. If we transmit and if we get a computed value, we can have an assurance that our ECU will detect that either the object is present or not. So it will be better if we have a multiple waveform, like reflection 1 and reflection 2. Like once the object is getting hit by the transmitted waveform frequency, the receiver frequency can be detected easily, right? So you will have a multiple reflections. So with that, this topic of how calculating the distance and velocity is done by radar, we have studied until now. And anyway, we have understand the science behind planting the crops, and now it's the time to seed the fruit, right? So let's discuss more about the application parts also. So I have already told you this part is used in autonomous vehicles and drones and many other weather forecasting also. This radar technology is used where the radar signal is getting transmitted in the open atmosphere, and in case of any droplets or any air movement, velocity is happening in the air and the atmosphere, it will get detected. So radio frequency will be received through antenna, and our meteorological department will be able to understand the movement of air, the velocity of wind, and the tidal winds can be calculated using this radar technology only. And there is one interesting application also which created an intention and motive for me to take this topic. So I will tell you now. So before that, we can have, like as I said before, we have an improved measurement of range and velocity, and range measurement, velocity measurement. So what I have said has been written here. So the frequency modulated continuous wave radar, upshift and downshift, where we can see the ups and downs, the crest and trough of the frequency, received frequency, refer to two phases of frequency modulation in the transmitted signal. Okay, these phases are used to create a triangular frequency speed which helps in measuring the range and velocity of the target. Yeah. So this is the basic functional block diagram which most of the automobile and the UAV means unmanned vehicles, right, like drones, will be using. So if you see here, there will be a waveform generator which which provides the pulse to the voltage controlled oscillator, pulse to amplifier. Okay, this will provide the signal to the transmitter, and that 90-degree mixer also. So this will compare, and once the transmitted waveform is received to the receiver, then it will compare with the mixture. So the mixture will just compare the transmitted waveform and the received waveform, and then it gets filtered using the ADC, analog to digital converter. So this digital output will give the digital signal processor to the ECU unit of the car and ECU unit of the drones. So based upon these values, this ECU will perform multiple calculations, and it will signal the radar and the motor system to drive the unit. So, and another important aspect of this detection and arranging is there are multiple waves, right, like ultrasonic waves, radar, radio waves and microwaves. So these each and every waveforms have a particular application and particular working, right. They have separate working, they have separate characteristics. So we will have a small discussion on this topic also. So this frequency range from, in case of radar, it ranges from 3 kHz to 300 GHz. So this means that it has a higher frequency. So lesser wavelength. The wavelength will be very less, but the frequency will be very high. And in case of ultrasonic, the frequency will be very less, but it has a higher wavelength. And in case of microwaves also, it has a very high frequency of similar to our frequency range of radar, radio waves. These microwaves also have the similar frequency range of 300 megahertz to 300 gigahertz. Even microwave frequencies are also used in our radar system, some of the radar systems also. Like I said before, the moisture directing system. So these can travel to a very high range, right? So it is widely used in our meteorological departments also. So application, as I said before, detection, tracking, aviation, weather forecasting, military, maritime navigation. So the invention of radars has been evolved from the World War II, right? So in continuation to that, even if you see the nose part of any aircraft have this transmission and receival system, which I will provide in coming slides. Like it is a vital part of any aircraft in military. So which will transmit and receive the signals in a very high fashion. So in ultrasonic sensors also, we will be also using ultrasonic in a short range distance, since the distance measurement and medical imaging, industrial and non-destructive testing, robotics. In the industry, non-destructive testing is a major thing. Like if you build a very big casting of a very huge size, like I previously worked on control wall industry, right? So I have experience like ultrasonic testing. So this any small cracks, any dents, any very small blowholes will be there in a huge casting. Let's say if there is any acid plant is there, and if you are providing a poor casting and if you are not tested with radiograph, it has in non-destructive testing there is another testing called radiographic testing, which is used for castings, and ultrasonic testing, which is used mainly for forgings. The forged part will be under ultrasonic testing. The ultrasonic waves will be transmitted through the metal part, and in case of any blowholes, like the frequency response graph will be taken and compared with the normal stainless steel. And if there is any abnormal change identified in the Fourier transform graph, then we can identify that there is some defect in the material, and if in case the defect is not captured, then it will create a big menace. Let's say if you are, like I said before, if there is any acid plant and if there is a casting or forgings of internal trim parts of control wall are the plug material and the seat material and inner parts, if it gone out means, then there can be an opportunity for accident also. So this NDT is a very big segment when ultrasonic testings are also used. So and in robotics also, ultrasonic for short range robots, and in case of humanoid robots also, ultrasonic testings are used. Similarly, microwaves, as I said before, in case of treatments also microwaves are widely used, like in case of cancer patients, in case of some like scans, it is also used in like intricate parts in the brain. So these uses radio waves and microwaves also. So the principle of operation and Doppler effect will remain the same to most of the waveforms, like send radio waves and receive echoes, emit high frequency sound waves and measures echoes, use microwave radiation for various applications. So similarly, Doppler effect is a major part and used in very wide industry, but the potential is certainly unknown till now to most of the engineers. So the main purpose of my topic is this only, to empower our engineers to know more about these radar technologies, sensor technology, how it is used, how the computation works. That's the understanding which we need, right? So the advantages resembles that it has a long range detection through clouds and rain, effective for short range, detects small objects, safe for medical use, high penetration capability, high speed data transmission. In microwaves also, data transmission is widely used, especially in the remote areas of any industries, the microwaves play a major part. And coming to the limitation, yes, each and every technology has its own advantage and limitation, and it can be eradicated through continuous research and development. Less effective for small objects, signal attenuation by atmosphere. So as a radar, you can see here, like for small objects like insects, birds, that kind of any objects, if in case if it is traveling, means it radio frequency cannot be detected. As I told before, the frequency traveled by the object will be very less, and the calculation will still remain a gray area. So in order to it is also one of the good thing for aircraft also. Like aircraft is not such a small thing, right? So it will detect aircrafts alone and removing errors like birds. And in case of ultrasonic, limited range performance affected by medium. Yeah, ultrasonic, as I told before, it is only used for short range detection. We will be using for Arduino projects and some other small projects and some other like remote vehicle robots, the delivery robots. These robots can be used like for pick and place robots. Those robots can also use ultrasonic waveforms. So in case of microwaves, as I told before, observed by atmospheric moisture leading to signal attenuation. So since as I told before, radio waves are used for transmitting and collection of data for the meteorology department, right? Microwaves cannot be used for that because it can be observed by the moisture leading to signal attenuation. This moisture in air also will get affected. So microwaves cannot be used in our automobile vehicles. Since if you are driving in a cold atmosphere and if the signal cannot be detected due to the so signal is getting disturbed by the moisture, then it will not work right. So radar, radio wave will be the best option in case of any rain or any kind of atmosphere near which the vehicle is surrounded with. So we will go through one more advantage. As I said earlier, hope you can guess the new age technology is the iron dome. So this why iron dome is such an important topic which I am picking into this, right? This iron dome can be a major thing which plays in today's geopolitics. So my lecture should be not be only about technical part. So Israel's iron dome is one of the major part. So hope the screen is visible now. So you can see in this picture, if it's not clear, we will go through some other pictures also. See, in the current scenario where in which there is high tension between Israelis and its neighbor nation, it is important to self-guard its own country. So Israeli has the radar technology which uses a iron, it just resembles the iron dome. Iron dome is nothing but iron castle. It's a dome inside, it's a cover which is put under Israel. Like if any enemies like missile, enemy aircraft, any unwanted activities is going to come to our region, then it will get affected. So this is such an interesting technology which each and every country is really puzzled, like how to attack any Israel, like even Palestine, Hamas and many other countries are really have a major challenge to attack this Israel technology of this iron dome. This iron dome was basically developed as a part of self-defense. So we will go through some of the like how it's working and how the radar technology works. We will go through it now. So this iron dome is an Israeli mobile missile defense system designed to intercept short-range rockets and artillery. Like as I said before, this is a remote technology that they can move from one place to another. Even if they having 2-3 equipments also, iron dome also, they can travel from one place to another. This iron dome can travel one place to another, thereby protecting each and every segment of our country. So it comprises lowest tier of Israel's missile defense architecture, intended to counter unguided rocket and drone attacks from Palestinian terrorists and Hezbollah controlled Lebanon. So there, as I said, same, right? It has detection and tracking radar to spot any incoming threats, weapon control. It has a battle management and weapon control system, and it has missile fire. It also missile firing unit. So it has both detection, control, and firing unit with it. So we will see the working of this Iron Dome now. So how it works? So it's a very simple thing which we can discuss now, but actually the real competition and the real backbone is completely unknown to most of people now. Even India is requesting Israel to provide this technology to safeguard from the enemy nations. So how it works? This whole process occurs within seconds, providing a rapid and effective defense against short-range threats. The Iron Dome is highly sophisticated, capable of handling multiple simultaneous threats and operating under various weather conditions. As I said before, a radar is one of the backbone of this technology. They can able to attack multiple missiles at one time, and this competition is happening just in not even less than seconds. So yeah, so we will go through step by step. Let's say if an enemy rocket is fired near to the Israel nation, so if they are firing, means the radar system detects rockets. This radar, as I told before, this is the starting point of any defense missile system of Iron Dome. So the radar detects the velocity and the range of the object, and the control system estimates control point, like where is the target can be launched, because it has to, the missile from our Israel team also have to travel and they should attack. So they will do the computation in a very fast manner. This control unit is also a part of the system, and it launches the fires missile, and the missile explodes near the rocket. So this missile will explode near the rocket. It will not directly attack, but it will explode near the rocket. So that by the big destruction can be avoided, and it can blown up in the air itself. As I shown in the first image itself, it will be like Diwali season to them, and they will be firing multiple rockets if any any harming rockets are coming. So operation success is about 85 to 97%. So they have a very good accuracy and towards the destroying another unmanned any terrorist attack. So they can able to defend themselves. As you can see here, the enemy missile will be destroyed at their base itself, in the air itself. The system has been deployed more than 2000 times and can protect, develop and maneuvering forces as well as forward operating base and urban areas against a wide range of indirect and direct aerial threats. So, but the only disadvantage is the radar system, it will be will be scanning only the high long range or very high distance. It can easily go through each and every. It will filter each and every part in the air. But in case if a missile attack in the lower space, lower altitude level itself, then it will be a big threat even for the nation also. So they are developing some of the strategies to prevent that also. So the Iron Dome is a missile defense system developed by Israel. It has a success rate of 85 to 97 intercepting incoming projectiles. The system has been operational since March 2011 and has successfully destroyed approximately 1500 rockets. The Iron Dome has intercepted over 300 missiles with a success rate of 90%. So as I said before, this is it's under development. It is developed in the March 2011. You can see the difference. Like initial radar was developed on the 1950s, and still now we are being dependent on the system. So how effective is still now? Yeah.
So it's a much reliable system where which we can depend on. So development and collaboration. As I said before, INDOM was developed by Israel's defense system and received support from the United States. The system is a part of Israel's border air defense strategy, which includes other systems like David Sling and Arrow. They also use some other systems like David Sling and Arrow, which can attack short-range missiles. So one of the criticism was the cost. As I said before, this war and other like any missile or any radar system for measuring a long range and doing multiple calculation, it will be a very costly thing, right? So say no to wars. Yeah. So with that, I am concluding my lecture on our radar system. So we will go through the conclusion part now. So as I said before, the effectiveness of radar is still now we are feeling, and if you see here the effectiveness, the technology advancement and versatility and future prospects and impact on society of radar. Okay, as I said before, the Doppler radar systems are highly effective in measuring the velocity, location of the moving objects. The continuous advancement in technology have enhanced accuracy and reliability. So this is not in words, but still I have also shown an example of how accuracy is maintained in defense technologies. It's all based upon the Doppler radar systems only. So about versatility and future prospects. The future prospects are still an ongoing development for India also. India is also developing in a very fast manner, especially in the defense technology, like many defense companies like Hindustan Aeronautics and Defense Research and Development, Department of Science and Technology. They are also putting hands with L&T Defense and some other local and private parties also to develop India's defense system. So, and it has a good impact on the public safety and disaster management. Like I said before, this radar system is not only for distracting someone, this is also a part of self-defense, and this is also used in many of the meteorological department. This radar system is also used in the automobile department for detecting the short range and long range distance and velocity, and in drones also it is a vital part of a radar system. So as I said before, it is better to avoid wars, and if we focus on the useful thing, we will have a good life. Thank you.